pesticide or bisphenol or caffeine. And the signal here is current, and the current generally is proportional to the concentration of target in the solution. And we can use this kind of material also to study oxidation of alcohol such as ethanol or methanol. So to modify how to modify our electrode, there is different compounds. So we can use bismuth film electrode. There are green electrode material which replace mercury film electrode. We can also use zeolite. Zeolite offer high surface area due to the microporous crystalline aluminum silicate materials, and also they can offer ion exchange capability and absorptive capacity. And conducting polymer also has been used lately for detection of various ion and molecules in aqueous solution due to their high conductivity. We can also modify the electrode with ionic liquids. Ionic liquids are used in different fields, and they offer several advantages such as thermal and chemical stability, and also moderate viscosity. And they are characterized by a low surface tension. And in electrochemistry, the ionic liquids are inactive with a large potential window. So the first example I will give you today, it's about electrochemical sensor based on low silica for carbaryl detection. And for this, we modify or prepare our electrode by mixing graphite with paraffin oil and 5% of low silica zeolite, and then the electrode was put in 3 electrochemical cells here with the target element. Of course, after preparation of the electrode was characterized by different techniques such as X-ray diffraction or other, and also by scanning electron microscopy, and of course by electrochemical technique characterization. And here we see the diagram of bar electrode and modified electrode with zeolite. And you can see that when we would modify our electrode, the current here increase, indicating that the electrical properties of carbon-based electrode are improved. The electrochemical impedance techniques confirm the results obtained by cyclic voltammetry, and here we see that the charge transfer resistance decrease when we modify our electrode with zeolite. So after that, the modified electrode was used for detection of carbaryl, and here we can see the response of our different electrode towards carbaryl, and we see here that the signal of carbaryl or the response on incurrence is increasing for about 35%. Of course, we optimize all the parameters such as concentration, pH, and potential of the deposition, of course. And under the optimized condition, a linear response was obtained in the range between 1 to 100 micromolar of carbaryl using differential pulse voltammetry. And here you can see the anodic peak or the well anodic peak corresponding to carbaryl detection. Now, of course, the reproducibility and stability and also the detection limit of the electrode was calculated. In order to evaluate the accuracy and the applicability of our method, we tried the sensor in food samples such as tomato sample and some additional methods. Oui. Est-ce que c'est bon? Vous arrivez à suivre? Je peux continuer?
Yes, yes,
Yes? Okay. So, the second example is about conducting polymer in liquids composite modified carbon-based electrode. And here is the mode of the modification of the electrode. It's very simple. We mix graphite with paraffin oil and appropriate amount of ionic liquids. And then we carried out the electropolymerization of our polymer. It's here. It's yes. And the film is formed on our electrode. So after I think there's problem with sound.
Yes, there is some problem with the sound.
I continue. So I continue.
Yes, it's okay.
It's okay? Okay. The characterization of the electrode was carried out after with the cyclic voltammetry and also with impedance technique. And we show that the introduction of ionic liquids composites increase the electron transfer rate at the entrance of electrode solution, and you observe the decrease of charge transfer resistance. So after the characterization of the electrode, the electrochemical behavior of carburet at different electrode was tested. I think that I have problem with sound. I don't know why. Samira, tu peux couper ton son, s'il vous plaît. Samira, tu peux couper le son. Voilà. Ça continue toujours? Non, c'est bon. OK. So, we study after that the response of modified electrode toward carburyl, and we see here that the best response is obtained with polymer modified electrode by ionic liquids. The best response was obtained at polymer film with an increase of 57%. The selectivity of the method of the proposed method was also investigated in the presence of different elements such as sodium, magnesium, calcium, and also other molecules such as ascorbic acid, hydroquinone, and capricorn. And the selectivity of the electrode method is the current remains stable and the selectivity is poor. The sensors was applied for detection of carburyl in spring water and in fruit sample with very good recovery. So if we compare the developed method with those in the literature, we can see that the modified electrode with silica, zeolite, and with polymer ionic liquids can give a very good response with a very low limit of detection, and the technique can be tested in different kinds of food matrix, also tomato, grapes, and also in water. Someone can please, there is problem in sound. So I just give two examples about carbon detection. So to improve sensitivity during the last decade, different approaches have been used to develop high-performance electrochemical sensor based on conducting polymers, carbon nanostructure, such as carbon nanotube, carbon nanofiber, and also graphene. So for this, the preparation of hybrid materials can be done by different ways. And in our laboratory, we are working on hybrid nanocomposite by using conducting polymers, carbon nanotube or carbon nanomaterials, and also metallic nanoparticles. We can combine different elements here. We can combine polymer with metallic nanoparticle, and also we can combine polymer with carbon nanotube or carbon nanofiber, and also graphene to obtain what we want as compound. So for preparing our electrode, different steps of the elaboration of the electrode are presented here. And here is our electrode. So after dispersion of carbon nanomaterials, we can carry out the electropolymerization of our polymer. For this, we can use polypyrrole, polyaniline, or polydiaminonaphthalene, or also polyparaffiniline diamine. And the polymerization can be carried out using different modes, cyclic voltammetry, potentiostatic mode, or also galvanostatic mode. And by using galvanostatic or potentiostatic mode, the time is very short to prepare our polymer. After that, we can deposit our metallic nanoparticle on the polymer, on the surface of the polymer. And we try to do we try to combine polypyrrole with carbon nanofibers or carbon nanotube. And the first example I will give you is about electrochemical determination of trace lead ion using a nanocomposite of polypyrrole carbon nanofibers. And here, so the carbon nanofiber was dispersed on the electrode surface. After that, after the suspension of carbon nanofiber on the surface of the electrode, the polymer was electrode deposited on the surface by galvanostatic mode using a current of 0.2 milliampere during 100 seconds. And the modified electrode was characterized by FTIR and XA-RI diffraction, also by cyclic voltammetry, electrochemical impedance, and scanning electron microscope. And the detection of lead was used, was the lead, or the method was applied for detection of lead, for determination of lead. And we have found that the sensor can detect lead at very low concentration. The second sensors prepared concern preparation and application of bismuth film combined with polymer and multi-walled carbon nanotube for simultaneous determination of cadmium and lead. And for this, we use the same strategy or the same approach. After deposition of carbon nanotube on the surface of the electrode, the polymerization was carried out, and the detection of lead and cadmium was performed by in situ electrochemical technique using bismuth film electrode. And as you know, the bismuth film electrode can form what we call alloy with lead and cadmium, and we can use what we call differential pulse voltammetry or anodic steeping voltammetry for detection of cadmium on lead. So after preparation of the electrode, here I present here the cyclic voltammetry obtained on different electrode. Here it's the bar electrode, it's carbon-based electrode, and the polymerization of polypyrrole on carbon-based electrode. And in blue, it's the polymerization of polypyrrole on multi-walled carbon nanotube. And you can see that the current is increasing when we use the electrode modified with multi-walled carbon nanotube. And also the impedance spectra shows that the electron transfer, the charge transfer resistance decrease here in the presence of multi-walled nanotube, even if the polymer is in a reduced form. So after the characterization of the electrode, and since our main objective is the application of the nanocomposite combined with bismuth particle as sensor material, the modified electrode was applied as sensor for simultaneous detection of trace of lead and cadmium using square wave anodic steeping voltammetry. And here I present the results obtained on different electrodes. Here it's carbon-based electrode. Second one, it's carbon-based electrode modified only with the polymer. The third one is the carbon-based modified with multi-walled carbon nanotube. And in green, it's the carbon-based modified with multi-walled carbon nanotube and polypyrrole. And the last one is the bismuth film polymer multi-walled carbon nanotube. And we can see that the combination of multi-walled carbon nanotube, polymers, and metallic nanoparticle can enhance the sensitivity of the electrode. And after the optimization of different electrodes, we can here see the voltammogram corresponding to the simultaneous determination of lead and cadmium using our sensor based on bismuth, polymers, and multi-walled carbon nanotube. Of course, when we develop sensor, we have to study the interference ions and also the stability of the sensor in sense of repeatability and reproducibility. And here we can see that the current remains stable even at a concentration in the presence of different elements such as sodium, calcium, magnesium, zinc, and iron. And the calculated relative standard deviation for cadmium and lead were about 2% respectively after 5 successive measurements using the same modified electrode. And the reproducibility of the measure of the sensor was also tested, and the relative standard deviation of the measurements obtained with 5 prepared electrodes was equal to 2.8 and 3.2% for cadmium and lead respectively, and the limit of detection as very low as you observe here. So, in conclusion of part 1, we have shown that the advantageous features of using polymer combined with carbon nanomaterial or metallic nanoparticles, and the developed electrode showed a good analytical performance toward lead and cadmium detection, primary detection with a very low limit of detection and good repeatability and reproducibility. And it holds good promise for its wide application in the determination of emerging pollutants such as bisphenol and pesticide in environmental and biological analysis. So in the first part, we see the electrochemical sensors. In the second part, since we know how to prepare different hybrid material, we study or the exploration of this material in energy. So, as you know, nanomaterial and nanocomposites offer a large surface area. They offer unique structure, good conductivity, and other spectacular property, and they are used in different fields. So, we try to apply our material for direct alcohol fuel cell, and for this we will study the methanol and ethanol oxidation. And if you take a look on a number of publications per year about direct methanol fuel cell and direct ethanol fuel cell, we can see that there is an increased number of publications about this topic. Why? Because the direct alcohol fuel cell have attracted much attention as one of the most viable candidates to replace batteries as source of water power, And among the various liquid fuels, ethanol is less toxic, has higher energy density, and easier to store and handle than methanol. I present here rapidly. You cannot see the movement, sorry. Yeah, I present here the principle of direct ethanol fuel cell. Direct ethanol fuel cell, in direct alcohol fuel cell, alcohol is oxidized with oxygen from air to form carbon dioxide and water to generate electricity. And the overall reaction at anode is this. So ethanol is converted to CO2, and overall reaction at cathode is O2 is converted to water. But what are the limitations of direct ethanol fuel cell? As you know, the most used catalyst for direct alcohol fuel cell is platinum. But this oxidation, it's now the oxidation of alcohol is relatively slow on platinum, and also platinum is contaminated by CO and or other space that can poison the electrode surface, and we have decrease of current, and the commercialization of this kind of material is limited by the high cost of platinum and palladium. So the main challenges is to prevent the formation in the case of ethanol fuel cell is to prevent acidic species such as acetaldehyde and acetic acid, and to maintain the catalyst activity. For this, huge effort have been done to reduce the use of precious metals, and we focus on non-noble metals such as nickel, copper, cobalt, and also to reduce the size. We can also combine carbon nanomaterial and polymer as supportive material with metallic nanoparticles. So the development of highly efficient catalysts using inexpensive and abundant metal is a crucial factor in a large-scale commercialization of direct ethanol fuel cell. And we study the first example I will give you here is about electrooxidation of methanol on carbon nanofiber and phenylenediamine and copper. Sorry, it's not nickel here, but copper electrode. So we explored a new catalyst. We have done the study with nickel and copper, and here I present the work done with copper. We explored new catalyst material based on copper dendrite supported on carbon nanofiber polymers, hybrid nanocomposite for methanol oxidation reaction. The nanocomposite catalyst support was prepared on carbon-based electrode using the direct electrophenolization of paraphenylenediamine monomer on a drop-cast carbon nanofiber network. Afterward, the carbon dendrite was electrode deposited on the nanocomposite to a potentiostatic mode. And here is preparation of the electrode. Simply, we can note here that the current on carbon nanofiber modified carbon-based electrode is increasing compared to polymer on carbon-based directly. And here is the deposition of copper at fixed potential of minus 0.5 volt during 45 seconds. And the morphology of the film was examined by scanning electron microscopy. And we can see that the morphology of carbon surface shows irregularly distributed flakes of graphite with a micrometer size. And the figure B here shows that the carbon nanofiber with a brush of diameter of 100 nanometer deposited on carbon-based electrode are uniformly dispersed, forming a carbon nanofiber network. And on C, we can see that a very thin film of polyphenyldiamine polymer is formed on the carbon nanofiber and connects the nanofibers. And the figure D and G displays the formation of three-dimensional copper dendrite nanostructure, and further examination of the electrode surface revealed that the dendrites have a hierarchical structure formed by multi-branch attached to a long axis. Of course, in order to To determine the phase of the copper deposited, characterization was performed by X-ray diffraction, and X-ray pattern shows the presence of two crystalline phases of copper, copper oxide and copper hydroxide. And of course, our electrodes are tested toward oxidation of methanol, and we can see here the response of the electrode modified with carbon nanofiber. Here we compare the response of different electrode, carbon nanofiber, polymer and copper, carbon nanofiber and copper, and polymer and copper, and you can see that the electrode check, what we call polymer, carbon nanofiber, copper shows superior catalytic activity toward methanol electrooxidation with current density of about 50 milliampere, while carbon nanofiber copper and polymer copper exhibit 40 and 36 milliampere by centimeter, respectively. So the carbon nanofiber increase the surface area, while the polymer present a large number of amine groups on the surface, which play an important role to improve the activity and durability of copper. Of course, here it's the concentration. The figure presents the variation of concentration of methanol, and we can see that we can reach concentration of 3 molar of methanol. We can oxidize 3 molar of methanol, and also the durability was tested using chronoamperometric method, and we can see that we have good stability in comparison with commercial platinum. Here is the commercial one. We can see that we have higher current density and more stability over 6 hours. So it's important, if we compare with reported catalysts in the literatures, it's important to point out that the developed catalysts show an improved catalytic activity compared to that of other previous reported catalysts. Moreover, our catalyst present a remarkable stability toward methanol oxidation reaction and was tested for 6 hours to provide complete information about the long-term stability. It's also noteworthy that polymer or composite forms were prepared by a rapid and simple way. So I give this example with methanol, but we have also prepared copper oxide particle on polypyrrole to study also its application, but in direct ethanol fuel cell. The advantages offered by ethanol is that ethanol is a good alternative to methanol. It's less toxic and it has a higher energy compared to methanol. And as liquid biofuel, the storage and the transportation of ethanol is less complicated and less energy consuming than hydrogen. But the challenges in direct ethanol fuel cell is to have a highly effective catalyst and also to facilitate the CC bond breaking or cleavage, also to enhance the CO tolerance and increase the ethanol conversion efficiency to CO2. And for this, we prepare 2 kinds of material, and we have using very creative approach with the activation of the surface of the electrode. So the first approach consists on the electropolymerization of the polymer using galvanostatic mode, 100 seconds, followed by potentiostatic electrodeposition of copper nanoparticle at fixed potential. And we study the reaction of ethanol on this kind of the electrode. And the second electrode or the second approach is the regeneration of the synthesis particle in acidic medium, followed by the redeposition of copper particle at constant potential. And here we can see that the dual pathway suggested for ethanol oxidation at platinum electron is this, it's C1 or we have acid structure and another diameter of around 1 micrometer. And the peak located here demonstrate that we have only copper oxide on the surface of the electrode. And we have studied the electrooxidation of ethanol using this kind of material. And we can see that the resistance of the electrode of copper oxide is really very important here. And the current observed is about 2 milliampere. And also we studied the effect of the concentration, and we can reach a very high concentration. We can oxidize until 5 molar of ethanol. And in order to study the stability of the resistance of our electrode, the effect of number of scans on the catalytic resistance on the polymer on the composite was studied and compared to the resistance of the platinum electrode. And here we can see that in platinum electrode we have a decrease in currents during cycling, while on the copper and polymer, the current is multiplied by, I think, by 3, and the current is very stable also. We can modify also the mode of preparation of the electrode by playing on the nature of the surface of the electrode. And here we can show that the regeneration of the particle was conducted, can play an important role on morphology on copper. And here we see the regeneration of the synthesis particle was conducted in acidic medium, followed by the deposition of copper particle at constant potential. And we can see here the difference between the two methods. We can compare figure here E and C. Without the regeneration of the catalyst, octahedral copper oxide particle were observed as our previous work. After the regeneration of the catalyst in acidic medium, we move from octahedral structure to dendritic structure. The change observed in film morphology is primarily attributed to the enhancement of conductivity of the polymer due to the application of anodic potential during the regeneration of the catalyst. So the nature of the surface plays a crucial role in controlling copper oxide routes. High conductivity of the surface leads to the formation of dendritic spaces. And you can see here the difference between the two electrodes. As can be seen, a higher current density was obtained at copper nanodontate compared to the first one, the catalyst prepared without regeneration of the electrode. And of course, for the real-world application of direct ethanol fuel cell, it's also required to study the long-term stability, validate the electrochemical performance of the electrode, and here the durability tests were performed with the aim of investigating the effect of regeneration of copper on stability of the catalyst. And here you can see that the current increase, and over 1000 cycles, the catalyst is stable and the current is maintained. We are conducting other study using infrared spectra or in situ infrared spectra to understand what happened at the surface of the electrode. And we can propose simply this mechanism on both electrode, on copper polymer carbon-based electrode. We have this, we can propose or suggest this kind of reaction. And on copper nanodontate polymer and copper, we can suggest that we have the complete reaction of ethanol to CO2. In conclusion, we can say that our work reports on a low-cost catalyst based on copper particles, supported on conducting polymers, which was synthesized on carbon-based electrode using a very simple electrochemical process. The nanocomposite were evaluated as an electrochemical sensor and also as catalyst for direct hydrogen fuel cell application. The catalyst materials are highly promising and can be good alternative to the novel metal-based catalyst and can contribute to the development of direct alcohol fuel cell operating in alkaline media. Further study in our group are underway to understand the mechanism of force of reaction and also explore this composite for energy storage application and CO2 reduction. Finally, I would thank all my colleagues and all my PhD students, my colleagues, Professor Alami Moussi, Dr. Label Olabdi, Professor Dr. ELRHAZI Halim, Professor Ibe Pero and Ozlem Seth from Sorbonne University, and all my PhD students, Anas, Nizha, Selena, Tariq, Saleh, Ewisal, and thank you very much for your kind attention.
Okay. Thank you, Professor ELRHAZI, for all the information and clarifications that you presented in your speech. We will now proceed with questions. Are there any questions?
Yes, from my side, if you allowed me.
Yes.
Yeah, thank
Please.
you. Okay, first of all, thank you for this nice talk and very important for the technology, either in for solar cells, for catalysis, and for sensors. And I just put here in the chat some remarks. Do you have any project regarding the potential of copper oxide as inorganic whole transport material for lead halide perovskite solar cell? Because copper oxide is a whole transport, not electron transport, and can be really a very good material instead of using very expensive organic compound which is used for perovskite. This one is inorganic compound. That's one thing, and if it's not, it will be good if there is a group in your from your side working on this topic, which is a very hot topic. Of course, in general, the transition metal oxide, not only copper but other transition metal, are important catalyst material for water splitting. And you know, actually, the photoelectrolysis of water using solar PV photovoltaic or emitting the native or artificial photosynthesis is very important. It's also another topic which can be matching your interest. Thank you. If you can make some comment on this.
Yes, thank you very much, Doctor. Yes, of course. There is many application of copper oxide, and we are thinking of. I asked already my student to work with phosphate because the colleague Professor Moussi, I am working with him, and Professor Abizan are working on phosphate and also on clay. And the idea is, of course, to have oxidation of alcohol on phosphate and copper oxide. For solar energy, I need, of course, cooperation with physicists. Probably I can do the material, but application of this material can be done with a lot of cooperation, of course. Concerning splitting water, yes, we can try also our material in splitting water, of course. Yeah, it's a very good idea, and we are talking about this. And also for nitrate, there is a lot of idea, but we need the first collaboration and cooperation with physicists. Second, funding, of course, we need funding for this also, and we respond to call of proposal of launched by ministry, the last call of, and we hope that we will have this project.
I think actually there are a lot of European projects just now, just call with Africa, and you should maybe look to the to this.
Yeah, okay, of course. If you can send me the link, yeah. We are working with Professor working on capacitors using our materials, and we developed, for example, for phenylenediamine, we developed material with very big capacity with the Sorbonne University. Yeah.
Thank you.
May I ask you one question?
Yes, please.
Yeah. Did you look at the size effect on the performance of the electrode? I mean, the size of the copper oxide and particles and so on.
Yes, yes, of course. We look for yes, and it depends, of course, for copper nano. The size of copper nanodendrites is more than that octahedral copper, and of course, when we have what we call small size, we have both best resistance. Yes.
Mm-hmm. Is that related because you have better exchange, because you have much more surface when you have a small size, or is it because, yeah, or because also because of the defect? Because defects are very important in materials, and if in fact they play a major role in their performance.
Yeah, I agree with you. And when I say that we are looking for understanding what's happened with copper nanodendrites, I think that the defect of the surface plays an important role. Yes, I think so. Yeah.
Okay, thank you so much. Thank you.
Thank you.
May I ask a question?
Yes.
Thank you very much.
Thank you.
Thank you for your excellent talk. And I would like to ask you if your detectors for heavy metals are suitable only in the case of water, or you can adopt them somehow for detection of heavy metals in airborne particulate matter. This question may be a stupid one, and another one, it's...
I don't, excuse me, I don't hear you. In liquid?
Excuse me, you would like me to repeat my
yeah.
Yes, simply I would like to know if your detectors are good only for the liquids, for finding heavy metals in water, for example, or you can also detect the particles, or to look at the heavy metals in particulate matter from the air. And another second question is how serious the problem of heavy metal is, in fact, in Morocco, in water and in the air. Maybe because, for example, in Poland now, okay, we have a lot of smoke, a lot of dust in air, but it is not so. There is not very much heavy metals in this. This is a mechanical problem, mechanical irritation of our organism. It is not very toxic in this traditional sense. But what are the levels of heavy metals in Morocco, in water and in the air? Okay, thank you very much.
Is there any question?
Just to tell you that I put in the chat the link for the European project. You can
Thank you, yes.
communicate it to the lady.
Thank you, Professor, for your question. Yeah, concerning impact of particle, of metallic nanoparticle, there is a lot of pollution, I think, in the world. I don't know if you heard about intoxication of lead in United States 4 years ago. So there's a lot of lead in water, in tap water, and until now there are problems with lead.
I see.
So,
Yes. Okay.
and I
So
think
the water
Morocco,
is the greater problem, I think.
yeah,
The water
it's
is more
very,
important.
yeah. They, of course, we can detect lead, but there is of course, as you know, the intoxication by lead can cause several damages in our system, in our neurological system, yeah, and lead what we call for children to, I don't know in English, it's Saturnism. I don't know, it in French is Satanism. I don't know, it's English, it's the same, because generally the heavy metals directly provoke some lesion in our brain by inhibiting some enzyme. For example, mercury inhibits the enzyme invertase. So there is neurological, what we can say, there is a lot of there's an example, of course, in Japan in the last in 1940 about intoxication by mercury. So we have to be aware about intoxication by lead, mercury, and heavy metals, of course.
Sure.
Yeah.
Thank you. Thank you very much.
Professor Samira, can I ask one question?
Yes, please, of course.
Thanks, Professor ELRHAZI, for this excellent presentations. I read your abstract, and you mentioned that you are preparing some sensors for COVID-19. Do you have some recent results? This is the first one.
Work, yeah, the idea is here. The idea is here because we can modify our electrode with conducting polymer and called nanoparticles, of course. Because in the literatures, there is a lot of paper about papillomavirus, the virus for I don't know, le cancer de l'utérus. And we are working to, of course, we need some collaboration with the biologists and also with the laboratory type P2 and P3, and we are looking for that. Of course, I have small projects about that, and we are looking for bibliography, of course, about that. Yeah. We can do it. I think that we can do it if we have all the elements. Yeah.
Yesterday, Professor Rahman from London University spoke about modelization and theoretical studies. Do you have some group?
Perhaps you can do it. Yeah, perhaps you can do it. Yeah, we can do the modelization with Professor Abdurrahman. Why not? Yeah, of course.
Thanks.
Professor Samira. Dear Professor Lamia,
Yes.
first thank you for this lecture, despite the sound quality. One of the participants, El-Bashiri Abdulrahim, asked, please can you justify the choice of your polymers?
So, sorry, can you?
Can you justify the choice of your polymers? What kind of polymers?
Yeah, we can use a lot of polymers, but in our laboratories, of course, we are looking for polymers containing amino group, because amino group can chelate, can form or can chelate what you make iron, metallic iron. So we are looking for polymer containing amino groups such as diaminonaphthalene or phenylendiamine or polypyrrole or also polyaniline. They are conductive, so we can measure current. We cannot choose non-conducting polymer on our surface, of course. But we can use other polymers now, for example, for detection of viruses. I know that a lot of people who are working on polymer containing the soufre S.
Yes.
Yeah. And of course, for detection of heavy metal for paraphenylendiamine, we looked for para, meta, and orthophenylendiamine, and we found that the best results was obtained with paraphenylendiamine, and perhaps we think that because there is a lot of amino group during electropolymization, only one amino group is involved in the formation of the polymer. So there is one amine which is free. They can form but bond with heavy metals with iron such Pb and cadmium also.
Okay, I think.
Merci. Thank you. Samira, le son. Samira, le son. Active le son.
Okay. That will be all for the questions. Thank you once again, Professor ELRHAZI, for your interesting topic. Thank you all for your kind attention. I will now hand it over to the organization committee. Thank you.
Merci.
Please, there is the last conference this evening for Professor Triki from Brest, France, and will be moderated by Professor Malk Fouad from the Department of Chemistry in our university. After then a quarter, welcome to follow this last conference.
Thank you very much.
Thank you so much.
Bye-bye.
Thank you.
أخت سميرة الله يجازيك بخير. أو good day. ديري شوية للصراحة ما كنسمع والو. Activate.
واه صافي جي اكتيفي. هو يعني غير داك لو بتي بروبليم ديال التكنيك اللي كان في الاول مي اوترومون الحمد لله لا كونفيرونس سيتي تري تري بيان ما شاء الله يا يو بوكو دو شوز. هو
مرة كيوقعوا هاد
وي سي نورمال
لي كاسيور هكاك.
وي سي نورمال.
Plaisir de vous voir donc.
Merci. Oui.
La troisième conférence. شكرا جزيلا.